Saturn, and Jupiter. How were they formed and evolved? And why we do not consider Pluto as a planet? And what do they tell us? The Kuiper Belt objects or trans-Newtonian objects about the origins and evolutions of the solar system. Okay, the reason we call it trans-Neptunian is because they are beyond the orbit of Neptune. Okay, and that's basically where you find the Kuiper Belt and many icy objects, most of them made of rock or ice, and quite small. Not necessarily the reason why, for example, Pluto is considered a dwarf planet, right? There are a few technical reasons, but it does make sense that Pluto and other Kuiper Belt objects have their own designation based on the proportions and the evolution of the solar system. Like we have the sun, we have the 4 terrestrial planets orbiting the sun quite close from the sun. Then we have the asteroid belt, and then we have the 4 Ovian planets. We studied Jupiter, Saturn, and their moons last week. And then we have the other 2 gas/ice giants, which are Uranus and Neptune. But then we have these other objects beyond the orbit of Neptune who do not really resemble either of the 2 classifications of planets, either terrestrial or Jovian. So that's part, not necessarily the main, but that's part of the reason why it makes sense to have another classification or designation for Pluto. Okay, so one of the first things that you should know is that the astronomer who discovered Uranus was William Herschel. You see him in the picture in front of you. He used a telescope, and in the 1700s is when he actually was able to visualize this object. He saw only a tiny green-blue dot, like it says there in the bullet notes. Now, he didn't know if it was a planet. He thought it could be a comet or maybe a star. It was a few years later that it was accepted to be a new planet discovered beyond the orbits of Jupiter and Saturn. And one of the reasons this was accepted was due to other observations from other astronomers, all of them using a telescope. So that's the thing about Uranus and the Neptune. You can only observe them through a telescope. You can observe with the naked eye Jupiter and Saturn, depending where you are located. And of course, the 4 terrestrial planets. But it's very difficult, almost impossible, to actually observe due to how far it is Uranus. So what we know about Uranus is that it's a very cold and very windy planet, kind of like what you would expect from a gas giant. Now, it's called an ice giant, surrounded by faint rings, 28 very small moons, and heavily tilted, as you can see in the picture, almost 90 degrees from the vertical axis. So it makes Uranus appear to be spinning sideways, right? It's still orbiting the sun, but it's spinning sideways. In terms of temperatures and pressures, is what you will expect from a Jovian planet. Okay, very extreme and very volatile for any type or any sort of organisms to actually exist or evolve or being able to adapt to that environment. One of the main characteristics that you should notice is the different color that you see in Uranus with respect to Saturn and Jupiter. With Saturn and Jupiter, we saw brownish, reddish, orange bands of clouds on top of where it will be the atmosphere of this of the planet. If you use infrared cameras, you can see bands, cloud of bands, like the ones in here. So one here, then one here, quite faint, and then one here. Here, you see these spots. They are actually storms, kind of resembling the big red spot of Jupiter. Not as big, but still, those are cloud slash storms happening on top of the in top of its atmosphere. Now, the difference of color has to do with the composition of the planet, right? Besides hydrogen and helium, it has a higher percentage of methane, right? Something that we don't find for sure in Jupiter and very little in Saturn, okay? So, why is this discovery so unexpected? Well, like it says in the slide, right? Why didn't Galileo expect to discover Jupiter's moons? It was basically due to what? It was predicted by them, right? So, sort of like an accident, because it was believed that the Earth was at the center of the solar system and every other planet was orbiting the Earth. So if you had that assumption, assuming that moons may orbit Jupiter or the other Jovian planets, were discovered as an accident, unexpected discoveries, right? Even though they are not the same as saying that it was an accident, it was something that was not predicted based on what they assumed, right? If they assume that only planets orbit the Earth and that no other worlds could orbit other planets, then it wasn't expected to discover moons orbiting, for example, in this case, Jupiter. Something similar could be said about Uranus. It wasn't expected to find another planet beyond the orbit of Saturn until we were the in terms of the size and distance, okay, the equatorial diameter, so where the equator should be or would be, it has about 51,000 kilometers of diameter. Just as a reference, the diameter of the Earth is 12,800. So that's about 4 times bigger, 4 times larger than the Earth. In terms of average distance, Uranus is about 19 AUs from the sun. So technically 18 AUs from us. Remember that 1 AU is about 150 million kilometers. So in terms of distance and time, it takes about 2 hours and 40 minutes for sunlight to arrive from the sun to Uranus. Again, just as a reference, it takes 8.5 minutes, as you know, for sunlight to arrive to our planet. We discussed how fast Saturn and Jupiter orbit around their axis, about 10 hours each, right? In the case of Uranus, due to differential rotation as well, is still a gas giant. It's a gas slash ice giant, but still mostly made of gas. So you will expect to spin very quickly. And that's the case. 1 day in Uranus is about 17 hours. So 7 hours less than our planet, but 7 hours more than Uranus and Jupiter and Saturn. Which is basically, as I said, the time it takes for Uranus to rotate around its axis. Now, however, Uranus takes about 84 years to travel to orbit the sun. Okay. And as you can see in there, right, Uranus rotates at about 98 degrees from the vertical axis. So the seasons are extreme. As it says there, or as you can see in the picture, when one of the poles is pointed towards the sun, then the person located at that pole will see the sun near the celestial pole. And just as you would expect from the North Pole, when you saw the Earth's orbital motion, the sun will never set for half its period around the sun. For a person who is on the other side, on the side that is not pointing towards the sun, here or here, then it will be basically only darkness, where the sun will never rise. Okay? So you have extreme seasons due to the extreme tilted axis of Uranus. All right. So as I said, the blue color in Uranus is due to methane. It's a hydrogen-rich atmosphere, however, with clouds of methane ice crystals. That's the reason why it looks blue. All right. And that's the reason why it's colder than Jupiter and Saturn. And the reason why you see bands of different colors on top of the atmosphere. All right. So telescopes like the ones we have here on Earth, or cameras from like the Voyager, they wouldn't be able to notice the clouds or the bands on the surface of Uranus. And when I mean surface, I'm talking about the atmospheric surface, all right? On the top of the atmosphere. With infrared cameras, however, we're able to visualize them more clearly, okay? So also, if you use computer processing softwares from different images taken from different flybys from Uranus, you are able to actually recognize these bands, as I show you in this picture. All right. The reason they are harder to visualize is because of the color of the planet itself, the temperature of the planet, and the differing in the composition of the planet. Right? Having a larger amount of methane crystals on the atmosphere will definitely make a difference with what we saw in the other two gas giants. And if you look at the graph of altitude versus temperature, you can see the comparison there, right? You see Jupiter, you see Saturn, and you can see Uranus and Neptune. Now, as expected, Uranus and Neptune, they have similar curves. They both have, especially Uranus, these methane clouds at around this altitude. And by the way, why is it below zero? Because we're going within the atmospheric section of the planet. Remember that if you make an analogy with the Earth, you have the core, you have the mantle, and then you have the whole atmosphere, all the different layers. If you go beyond the layers of the upper atmosphere, you start entering where the mantle should be. But these planets do not have a rocky mantle. They are all made of different composition of hydrogen, helium, or other gases. So as you go beyond the upper atmosphere, that's when you start going below zero. So that's basically where the mantle should be. That's where you find the methane clouds. And it makes sense that they are there because they are heavier elements. It's a heavier compound, heavier than hydrogen and helium for sure. So it makes sense that you can find them there. So in terms of temperature, you can see that Uranus has a range of about 190 kelvins, to about 100 kelvins, right? So in Fahrenheit, we're looking at negative 150 to negative 300. Quite cold, right? That's why I said, and you can clearly see in the graph, Uranus and in some to be colder than Saturn and Jupiter. The difference is that Uranus is always colder. Neptune is colder, but at higher altitudes, it starts to become warmer, right? As you can see in this section here. Okay. So look at this dark cloud that may be a circulating storm. This was an image from the Hubble telescope. So the Hubble telescope allows us to have a better angular resolution and gathering power to actually being able to get a more clear picture and with more detail about these bands that we know exist on the upper atmosphere of Uranus. All right, which is why they call it changing clouds, by the way. So what about the interior, right? Well, as you will, as expected, it has a very low density, around 1,300, 1.3 grams per centimeter cube, or 1,300 kilograms per meter cube. It does seem to have a larger portion of rock and ice than the other two massive gas giants, especially having a larger portion of ice. That is key in the difference or to illustrate the difference with the other two gas giants. Where the mantle should be, you find gases, but you also find methane clouds, ammonia, hydrogen, and slushy water. Not water per se, but it's just the composition in the mantle, in what should be the mantle of the planet. And you have a heavy element core, not an iron core, but heavy element. And this may be due to the different composition and the ice present in the upper and lower atmosphere of Uranus. Okay, so just there you can notice a difference between the interiors of Jupiter and Saturn and Uranus and Neptune, right? Jupiter and Saturn in the interior, they're mostly made of rock, about the size of the Earth, or maybe a little bit bigger, surrounded by liquid metallic hydrogen, and then surrounding on the upper atmosphere of hydrogen gas. And you have all those clouds, and the different composition and the different color of those clouds. The same can be said about Saturn, with the difference that Saturn has more helium inside a planet. And as I said last class, it may be due to raining helium from the upper atmosphere, right? Or it's due to that, by the way. We know it's because of that. So Jupiter and Saturn are mostly liquid hydrogen. Uranus and Neptune are mostly solid water ice giants. So what is this trying to say? That we call them gas giants, which is the accepted name, but in astronomy, we normally call them the Jovian planets, because calling them gas giants can be a bit misleading. Yes, they have a large amount of hydrogen and helium gas, but that's normally just on the upper atmosphere. Below, where the mantle and the nuke and the core are, there is no gas. It is, as it says there, right? Liquid metallic hydrogen for Jupiter and Saturn, and ices or ice, solid water, where the mantle should be in the case of Uranus and Neptune. So you still find gases. It's just that the proportion of gases in those planets is not the largest, right? However, it's what we see, right? When we are taking pictures of these planets, we normally take snapshots of the upper atmosphere. And that's what we have analyzed the most thanks to spectroscopy. So the sunlight bounces back from the upper atmosphere. So we tend to investigate mostly the composition of the gas surrounding those planets. But when we take more, thanks to the Galileo, the Cassini, right, the Voyagers, we have been able to explore these planets with more detail and analyze the interiors and compositions with more detail, which have allowed us to correct these misconceptions. So in terms of magnetic fields, you can see that the magnetic field for Jupiter is quite large by the lines that you see there. The same can be said about Saturn. Uranus and Neptune, they also have magnetic fields, right? But it's very unusual. In the case of Uranus, it's irregularly shaped, right? Look at the left-hand side and the right-hand side. There's not really a symmetry like you will expect from a magnet. The magnetic fields are normally aligned with the planet's rotation. We notice that for the Earth, we notice that for Jupiter and Saturn, as you can see in the picture there. But for Uranus, magnetic field is a little bit tipped over. So the magnetic axis is about 60 degrees tilted from the axis of rotation. In the case of the Earth, for example, it's just about 3 to 4 degrees tilted from the axis of rotation of the Earth. So that's what I'm saying. It's very atypical, right? Now, we know it has a magnetic field, so Uranus has auroras. But they're not going to be in the poles because of this tilt, right? The magnetosphere behind Uranus, opposite to the sun, extends into space for millions of miles. All right. So we do see auroras for Uranus, but they are not located in the north or southern pole because of these magnetic field lines and the way this magnetic field is produced. It's still produced by metals orbiting very quickly inside the planet, right? But it's not as strong as the other two gas giants, or Jupiter and Saturn. Okay? So there is a dynamo effect. Remember, dynamo effect is the idea behind the magnetic field of planets like the Earth, Jupiter, Saturn, and now Uranus and Neptune. But the dynamo effect in Uranus and Neptune is quite different to the one that we have seen for the other planets, especially the Earth. So that's where the auroras are located. Yeah, you could say that they are close to the southern pole, but not necessarily, right? Look at the picture on the right. Those were taken by the Voyager 2 in 1986. Okay. Again, remember that the magnetic field is very tilted due to its, well, basically due to the planet's tilted axis. That for sure had to play a large role in why the magnetic field axis is as tilted as it is. Okay. Okay, so we've been talking about Uranus, and sometimes we mention surface. Just like the other two gas giants, Uranus doesn't have a true surface. It's mostly thrilling fluids or ice, solid water. So a spacecraft will have nowhere to land on Uranus. It wouldn't be able to fly through its atmosphere either because of extreme pressure and temperature values that will destroy, basically disintegrate the spacecraft. Sort of what we noticed with the Galileo when they launched it towards Saturn or Jupiter. Jupiter. at the end of this mission. In terms of atmosphere, remember, Uranus' atmosphere is mostly hydrogen and helium. That's true for the upper atmosphere, with a small amount of methane and some traces of water and ammonia, NH3. The blue color is because of methane. Remember that. Rings. Uranus has two sets of faint rings. The inner one has 9 rings, very narrow, mostly made of ice and crystals. And then the innermost one is reddish, mostly made of dusty rings. Okay, so it does have rings, and they also follow the Roche limit. Okay, which is a position where that can be in a stable orbit without being disintegrated by tidal forces of the planet. In terms of moons, Uranus, as I said, has 28 moons. Now, most of the satellites in the solar system, they take the names from the Greek and Roman mythology. Well, Romans took over Greece, and that's why you see a lot of Roman names, right? Uranus moons are unique in name because they were actually the work of William Shakespeare, believe it or not, and Alexander Pope. All right. All of Uranus' inner moons appear to be half water ice, half rock. And the composition of the outer moons is still unknown, but they seem to be captured asteroids, so mostly rock and metal, maybe. All right. And you see there's some names in there. Ariel, Titania, Umbriel, Miranda, and clearly the rings in there, right? This is an infrared picture there. All right. So here is what I was talking about, the composition of the moons, ice and rock, some of the diameters in there. Not as big as our moon, and at least some of them. And of course, the Galilean moons, or the largest moons of Saturn, still though, right? A planet like this is expected to have quite a few moons. And when you start seeing these moons, you start seeing the resemblance with Pluto. They do resemble an icy object like Pluto, right? There's not much to say about these moons. It's not like the moons of Jupiter and Saturn. If they have ice and rock, that will be it. There's no evidence of water in these moons or any sort of atmosphere for us to think that there might be interesting things that we can find. Like, for example, we discussed last week with moons like Titan, Ganymede, Europa, Enceladus, where there are potentials to find life, right? Now, of course, we keep sending missions to the outer parts of the solar system. So we keep finding, for example, 2 newly discovered rings orbiting Uranus. This, by the way, I don't know if you guys can see it there, right? Even though we had flybys in the 80s and 90s, the quality of the cameras were not as good as the ones that we have nowadays. And nowadays we have very powerful telescopes that can allow us to visualize these planets and get more detail that was obscure a few decades ago. And I think here in this previous slide, it says that, not there, here, 22 more moons have been discovered. Well, I mean, 22 plus 5, 27, right? So yeah, 28. So yeah, we discovered a few moons at the beginning, but then 22 more were discovered right after, all right, with higher resolution images. Okay, so in terms of the formation, It's not surprising that they were formed closer to the sun, guys. Remember that the origins of the solar system, the model suggests that Jupiter was formed first, right after Saturn, which stopped Jupiter's migration towards the sun. But then you had Uranus and Neptune forming closer to the sun in the neighborhood of the other two planets. Gravitational interactions, and in the last instances of the formation of the solar system, when the sun totally became a T Tauri star, basically igniting in the process of its ignition, that is when these planets were dragged towards the back part, you want to call it like that, right? Towards the back of the solar system. All right. The highly inclined axis is most likely due to a planet collision, just like we had it in our planet that formed the moon. Debris from those impacts on moons could be the source of rain, by the way. So that impact should have of Uranus. It probably, the debris of that collision may have formed the rings that we see orbiting around Uranus. And that's basically it for Uranus, not much, right? I mean, there are a few things interesting here and there, the comparisons with the other planets, but other than that, it's a planet that is there, that we care about because it was found. It was the first planet to be found with a telescope. And now we're going to look at another planet that wasn't really found with a telescope, right? Because right after Uranus was discovered, we knew where it should be orbiting. So we were able to place it beyond the orbit of Saturn in a model of, in a very ancient model of the solar system. But then by doing some math, using Kepler's laws, for example, by looking at the gravitational perturbations in Uranus, especially on the moons and the rings, we predicted, or it was predicted, that there should be another planet or a planet-sized object orbiting beyond the orbit of Uranus. That is how we predicted that Neptune should exist. Because there should be a similar size and density planet to Uranus orbiting the sun at a farther distance, of course. So it was the first planet that was located / discovered through mathematical predictions or calculations. These calculations were made by Urbain Le Verrier. And then Johann Galle discovered the planet in the 1800s, 1846 to be more precise. The planet is named after the Roman god of the sea, suggested by Le Verrier. So yeah, that's all in there. All right. And that's what we see. Again, we can take pictures using an optical telescope, like the ones you can get for your house. Not any telescope you can buy is a visual telescope. But then if you use an infrared camera, you start seeing that Neptune is a dark cold, wiped by very strong winds, is still an ice giant, and not able to be seen with a naked eye. Neptune is so far from the sun that high noon on this blue planet will seem like dim twilight to us because of how far it is. The warm light we see here in our planet is about 900 times as bright as the sunlight on Neptune. That's because of the inverse square law. The farther you are, the lower the intensity by a power of 2, distance squared. That's the inverse square law for intensity. Okay? So that's the reason why Neptune and Uranus are very cold. They are too far from the sun. You see blue-green colors as well in this planet because of methane and a hydrogen-rich atmosphere with, again, clouds of methane ice like Uranus. You also see cloud belts with very high winds. In some cases, storms of hurricanes can also be formed on the upper atmosphere. In terms of its size, it has a diameter of about 50,000 kilometers, so about 3.5, 4 times the size of our planet. It's about 30 AUs. So this is the thing about the scale of the Jovian planets. It was 19 AUs for Uranus, 30 AUs for Neptune. Just as a reference, the distance between the sun and the earth is 1 AU. And between the sun and the earth, there is Venus and Mercury. And between the sun and Mars is about 1.5 AU. Right? So the terrestrial planets are all orbiting very close to each other and close to the sun. However, for these planets is totally different. Okay? At that distance, it takes about 4 hours for the sunlight to reach the planet. A day in Neptune takes about 16 hours. So it's also orbiting quite fast or more rapidly than the Earth. And it takes about 165 years for this planet to orbit the sun. Now, this is interesting, and this is something that you guys notice in the first lab. Sometimes Neptune is even farther from the sun than Uranus and Pluto. Well, than Uranus makes sense. But sometimes it's farther than Pluto. How is that possible, though? If Pluto is a dwarf planet that is in the Kuiper belt, beyond the orbit of Neptune, it's because Pluto has a very high eccentric orbit, meaning it's very elliptical, which basically brings it inside the orbit of Neptune for a 20-year period every 250 years. You may be thinking, what's the probability of them crashing? Probably very low, because it would have happened by now, and because of gravitational synchronization, right? So there is a synchronization that maybe avoids, not maybe, that most likely avoids the planets from interact with one another, right? The switch, the last time we saw this switch happened in 1979 to 1999. During those 20 years, Pluto's orbit was closer to the sun than Neptune. So, well, yeah, the explanation for why Pluto cannot crash into Neptune is because of gravitational synchronization, which has allowed that Neptune and Pluto, they take different laps around the sun. For every 3 laps Neptune takes around the sun, Pluto does 1 lap. So that is actually a constant. So that is basically the reason that they never collide. In terms of the tilt, Neptune has a similar tilt to us. Our tilt is 23.5 degrees. The tilt of Neptune is about 28 degrees. Okay, with respect to the vertical axis. And in terms of moons, Neptune also has moons and rings, but very faint rings, only 16 moons. What's interesting about Neptune is what you are seeing there. Is this dark cyclonic disturbance that resembles the red spot of Jupiter. In this case, we call it the great dark spot. All right. There you have. So what about the composition. So Neptune is also a nice giant, all right? About 80% of the planet's mass is made up of hot, dense, icy materials, as like water ice, methane, and ammonia. And just like the other Jovian planets, it has a small, well, maybe bigger than the other ones, rocky core. Out of the 4 Jovian planets, Neptune is the most dense. So it has heavier elements and a higher value and a higher proportion of a rocky core than the other planets. It's believed that there may be an ocean of super hot water under Neptune called clouds. And it doesn't boil away because of the very high pressure locking it inside. That's what is believed. There's no evidence yet for that. Again, because most of the information that we get is from the upper atmosphere, which, yeah, the atmosphere, right, is mostly made of hydrogen and helium, like the other Jovian planets, with just a little bit of methane, all right, just like Uranus. Methane absorbs other colors but reflects blue. That's the reason why we see it blue. The same for Uranus, okay? Most of the information from these planets come from the Voyagers, especially Voyager 2, which was launched in the 1980s and arrived and fly by these planets in 1989. In terms of winds, Neptune is the windiest planet of the solar system, right? Even though it's at a very large distance from the sun, and it has a very low intensity or very low energy from the sun striking the planet, Neptune winds can be 3 times as strong as the ones in Jupiter, and 9 times as strong as the ones on Earth. So whenever you complain about wind or hurricanes, think that there is a planet in the solar system that has 9 times the wind velocities that we have here on Earth. These winds are basically because of the frozen methane across the planet that speeds for more than 1,200 miles per hour. All right. Just like the other planets, there is a magnetic field, but it's not generated in the core. It's generated in the mantle. All right. And heat may be generated by radioactive decay in the minerals in the interior. So there are minerals, there are heavier metals in the interior, which increase the density of this planet. Okay. Remember, the axis of Neptune is tilted. And like Uranus, the magnetic axis for Neptune is also tilted. Now, this magnetic axis, this magnetic field in Neptune, is about 27 times more powerful than that of the Earth. The magnetic field of Neptune, by the way, is tilted about 47 degrees from the axis of rotation of Neptune. It was 60 for Uranus, so kind of comparable. The most important moon for Neptune is Triton. Okay, it's the largest moon. By the way, you can see the very eccentric orbit of one of the moons, right? That's what I mean by eccentricity. It's how elliptical it is. Why is Triton so important? Because it's considered a very active moon. All right, as it says there, the frozen nitrogen in the polar caps appears to be vaporizing. All right. So we see nitrogen geysers, something that we didn't see with the other moons, right, from Uranus and Neptune, which are basically geologically dead. So there is some activity in this moon. In terms of rings, just like Uranus, you have some small ices and rock and also dust particles that are scattered, right? Forming the rings of Uranus. And we can see how some of these produce arcs. You have the inner and outermost rings. So that's kind of similar to what we saw for Uranus, right? And then when we talk about Neptune, just like Uranus, remember that one of the differences is the significant amount of heat produced in the interior by different minerals in the interior. That's the difference between Neptune and Uranus. The rest, you can say that they are very similar in terms of their composition and color, of course. And well, another difference is that Neptune is not tilted as Uranus. But that's more like an external factor, right? It's not due to the formation of the planet per se. So that is those are the facts and the information that you should know regarding Uranus and Neptune. Now, it's not over because once we discover these 8 planets that we have talked about, right? The 4 terrestrial and the 4 Jovian planets, we start introducing what's beyond the orbit of Neptune. Here is when we start investigating the Kuiper belt and the trans-Neptunian objects, which are these icy objects which resemble comets orbiting the sun in very elliptical orbits, which is the reason why Pluto is very elliptical, has a very high eccentricity, because it's part of these icy objects that are orbiting beyond the orbit of Neptune. Now remember, when we studied the formation of our planet, I spoke about the formation of the oceans. And the theory, the prevalent model and theory, or the accepted theory, is that comets in the early heavy bombardment and late heavy bombardment of the planet is what brought minerals and water, dirty ice, to our planet that melted and formed the oceans. But the source of these comets was an issue up until we discovered the Kuiper belt, which is these icy objects located beyond the orbit of Neptune. One of those objects will be Pluto, discovered in 1930, about 100 years ago. All right. It says that he found a 15 magnitude image. You should know that the larger the magnitude, the lower the brightness, right? So it was a very, very faint object beyond the orbit of Neptune. The astronomer was Tombaugh. He was an American astronomer. And when he discovered it, it was accepted to be the 9th planet of the solar system. In 2006, the International Astronomy Union redesignated or renamed Pluto as a dwarf planet because there was a particular characteristic that Pluto had that the other planets didn't, which was that its orbit was surrounded by many, many icy objects that could be also considered planets because they are also orbiting the sun. Now, some of them, for example, Charon is orbiting Pluto, so we normally say that that's the moon of Pluto, right? But some of those objects are like small comets, right? Made mostly of ice. So, because of the size and because of the way it's orbiting the sun, Pluto can be confused as a planet. But because of its orbit, because of where it's orbiting, and if you think about it, right, because of the composition of Pluto itself, it was reclassified as a dwarf planet. Oh, by the way, guys, there's a picture here. All right. there has been a huge amount of investigation from New Horizons. There's a flyby to Pluto a few years ago, taking very, very detailed pictures of Pluto. Difficult to observe from the Earth, very eccentric orbit, a surface of solid nitrogen, ice, with temperatures of 55 kelvins. The absolute zero is 0 kelvins. So look how cold this planet is. Very dramatic seasons. I mean, you can call them seasons. And significant amount of albedo. What's albedo? Is how much light, sunlight is reflected. Right? Venus has a higher albedo than the Earth. That's why you can normally see Venus very bright in the night sky or in the morning, because it has a very high albedo because of the atmosphere. Right? The reason why Pluto has an albedo is because apparently it has a very thin atmosphere. All right. And we're going to finish by introducing the family of dwarf planets, which are located in the Kuiper belt. That's when we start investigating dwarf planets. So that's what we're going to be talking in our last lecture next week. We're going to be talking about something about comets and asteroids to finish with planetary astronomy. All right. There is no more labs. I'll be grading your lab, the Mars lab, between today and tomorrow. Right now, I'm going to open the quiz. Yeah, it's already open there. That's the last quiz for this semester. So please, you can start working on it right after class. All right, that's perfect timing. Are there any questions about what's coming next or at the end of the semester? Okay, so guys, I hope you guys have a very nice Thanksgiving. If you have any questions, I'm gonna be checking my email tomorrow and then on Saturday and maybe Sunday. Okay. Other than that, we're gonna meet again next week, and that will be it. All right. Uh, Feel free to start working on the quiz. I'm gonna be checking it tonight as well. All right.
Professor, I sent you a chat.
Oh, this is about the sky charts.
No, I was asking if class next Thursday is online.
Yeah, it's already online.
Okay, perfect. Thank you. Have a nice Thanksgiving.
Yeah, you too. Thank you.
Thank you.
Professor, question.
Yeah.
Wait, so next class is online, you said?
Next class, yeah, it's gonna be online. Next class is
Okay,
online.
so from starting this week, everything is online?
Yeah, well, there's no class on Thursday, and we have a class on Tuesday. And then the exam free will be online next Thursday.
Is the quiz posted?
Yeah.
Okay.
I don't see the quiz.
Quiz 5. You said?
Okay, yeah, I see. It's due next week, right?
Yeah, no, it's due tomorrow. I just changed it.
Okay.
Professor, another question?
Yeah.
For the sky charts lab. So for me to fill them in,